All right. Good morning, everyone. So, welcome to today's tutorial. This is co-organized with Love Varshney. And I have to admit, this is my first visit to ISIT. I really appreciate being here. Usually, my conferences that I go to are in the circuits and systems area. So I really feel privileged to come and visit this particular symposium. Today's tutorial that Love and I have put together has, if there's one thing that I want you to remember at the end of the tutorial is the following, that today in the world of integrated circuits and systems, there is almost an existential crisis. And this crisis has come about because we have reduced the size of our devices to such a small values that the circuit fabric and device fabrics are becoming stochastic in nature. So while the society is demanding more and more compute power, but they want to achieve all of that with much higher, greater levels of energy efficiency, all right? And so we are reaching a point where the circuit fabric is becoming stochastic in nature, and we are not really well equipped to handle that stochasticity. And this is where I believe that the role of information theorists comes in handy. So there's a big demand, huge demand in the circuits and systems area for folks like yourself who can bring your analytical background and analytical strengths in statistical inference and information theoretic analysis and show us how we can build systems of the future. So I want to begin by giving you a background of why did we come to this point, the motivation for this tutorial. So we'll start off with the realization that machines are in fact becoming quite powerful. We have seen all of these news items in media. In fact, if you scope down the problem sufficiently and provide sufficient data, storage, and compute resources, you can achieve these amazing results. But what is not talked about is that there's a huge energy cost involved. So a lot of these reports don't mention that the gap between what this human can do and what that machine has been able to do, that there's a huge about 3 to 4 orders of magnitude gap in energy efficiency between these two systems. So this is okay if you're in the cloud. Maybe it is okay if you're settled in a cloud-based platform. But if you want to bring intelligence into these at the edge, platforms that are at the edge, then we are faced with platforms which have very low form factor, small form factor, constrained volume, constrained energy, but of course, data rich. So these platforms are data rich, but they don't have enough compute power, enough storage power. And so we have to figure out a way to bring all of that intelligence into the swarm. We use the term swarm or the edge. And doing that is a big challenge, a huge challenge, because in all of these applications, extracting information costs a lot of energy, all right? And so we have to figure out a way to minimize it. So the fundamental question that we face today is how do we build these computing systems of the future which need to operate at the limits of energy efficiency. And we will see later that this term energy is synonymous with latency. So in circuits, energy, latency, and accuracy. Those three metrics, they trade off with each other. It does not matter which circuit you're looking at, which technology you're looking at. If you try to reduce energy, you have to pay the price, and that price is usually in terms of the delay of computation or the accuracy of computation. And so that's the Pareto optimal surface we need to determine and operate at. So in the past, and even today, how have we built computing systems? We have always built it up bottom up. We have asked the device researchers to give us new nanoscale devices. We model them as ideal switches, and then using those switches, we put together an architecture, usually a von Neumann architecture, and then we map applications to those. So in building today's computing systems, we are literally suppressing the statistics of the switch in order to build deterministic computing systems. And this suppression of statistics has worked well so far. For the last 50 years, it has worked extremely well. But today, as we reach the limits of scaling, the semiconductor industry is worried, how will we get that next jump? How can we get that next device? And so Moore's law for the last 50 years, 1965 was the paper that Gordon Moore wrote, in which he predicted that the nascent semiconductor industry will be able to will be able to double the number of transistors per unit area every 18 months. And today that 18 months has become 24 months. And if you look at some of the articles out there in media, you'll find that length has grown even more. Why? Because it is extremely difficult to scale down devices while preserving the accuracy, while providing the energy efficiency that we are interested in. So this Moore's law has been sustained over the last 50 years. It is used by industry to benchmark its progress. So if a particular company doesn't meet that benchmark, then it's not considered good. And it's a huge industry. The revenues projected by the Semiconductor Industry Association is about more than $400 billion per year. So it's a huge industry, and there's a lot of concern that we may be reaching a point of diminishing returns. And so a lot of folks have studied this and have shown that unlike in the previous years, when you go from one technology node to the next, we automatically assume that you will get an energy efficiency boost, you'll get a speed up, and increase in integration density. You can pack more functions in the same area, right? So all three things have to be obtained. Today, you get integration density, but you don't get energy efficiency boost, right? So this is a big concern. And furthermore, it is becoming difficult to handle the variability. As you make devices small, those statistical variations, they are much harder to suppress. That's at the lowest level, at the nanoscale level. At the compute level, at the architectural level, we have been using the von Neumann architecture since 1945, when it was first proposed. In the von Neumann architecture, there is a separation between memory and compute. And this has always created a problem for computing in general, because you have to read a lot of data. To do computation, you have to read data from memory, process, and provide the outputs. And this reading of data from memory consumes a lot of energy. In fact, recent estimates show anywhere from 10x to 100 for on-chip memory. If you go off-chip, these numbers become even bigger, 500 to 1000x, which means you read 1 byte of data from memory, you bring it in, and you already have consumed 1000x more energy than the energy required to do multiply add on that byte of data. In the past, people have created, the computer architects have created a very complex memory hierarchy to handle this problem. But with data-centric workloads, with machine learning workloads today, the traffic that we see between memory and processor is amplified. And this problem, the energy problem and the latency problem, both have been totally blown out of proportion. It has it has hit the roof. So we don't have a good architecture at the highest level to manage the energy problem because of the separation between memory and processing. And at the lowest level, we don't have this silver bullet that came from Moore's law. Every generation, the semiconductor industry gave us this beautiful new technology node, and we went ahead and built systems out of those. We don't have that assurance anymore. So the reason these two problems coexist is because the von Neumann architecture and the computing systems we build, they are deterministic in nature. And we are asking the semiconductor industry to suppress that statistics, to hide it so that we can continue to do what we did before. Now, the cost of preserving determinism has become very large, and this is a good example here. Spintronics is another device, a new nanoscale device that is being explored. If you run it in the deterministic regime, then, by the way, this is energy on the y-axis and delay on the x-axis. So those are the two important metrics when it comes to integrated circuits. CMOS, which is your mainstream technology, lies somewhere here. And so we would like to build systems which lie closer to the origin, so that delay is minimized, energy is minimized. But with Spintronics, if you run it in the deterministic regime, it is not even competitive with today's CMOS. CMOS is what industry is already doing. They know how to build, CMOS technology. So we want to be operating there, and if you operate there, it turns out that the spin device is stochastic in nature. It behaves probabilistically. And we don't know how to build reliable computing systems with probabilistic gates, with probabilistic devices so far. But you'll hear from Love later today, this morning, how to do that using Shannon-inspired ideas. And similar properties we observe in RRAM, resistive RAM, where when you program it to achieve a certain resistance, that resistance value is a random variable, right? And so how can I build a reliable system in which I expect all of my resistors to achieve a certain value, but there is a variation around it, and that variation keeps increasing, all right? So this is a real issue, real problem. And if you look deeper down, if you actually go down to the device level and look at the fundamental switching mechanisms, you will find that there is a fundamental trade-off between energy and accuracy and delay. So energy, delay, accuracy, at the fundamental switching level, they trade off with each other. And so far, we have broken this loop by having a very high SNR circuit fabric. So in the world of integrated circuits, we deal with high signal-to-noise ratio circuits, so that we don't have to worry about probability of error caused by circuits. And the price we pay is in terms of latency and energy. And this price we cannot afford to pay. So we are asking this question, what else is out there? What can we do better? So we need to figure out ways to design reliable systems using unreliable components. And in fact, it turns out, this is quite familiar to you, given your backgrounds, that you can build, you can have a reliable data communication over a noisy channel. And Shannon showed the limits of that communication channel. And the brain at the other extreme, we know it's not a von Neumann architecture. We know that the neural fabric is non-deterministic, yet we see sort of reliable outputs, system outputs coming from both of these systems. So what's common to these two is that both systems are built using stochastic components, but they use statistical models of computation. And somehow we have to couple the two together in the world of semiconductors to create this next revolution in the design of these systems. So how do we do this in a principled manner? This is what this tutorial is about. Now, the move towards non-determinism in computing has actually a long history. The more recent ones are shown here. There was a paper that my group had written in 1997, where we made the claim, the statement that integrated circuit should be viewed as a network of communication channels. So this is where integrated circuit is reaching out into the world of communications. And then in 2001 and 2003, the International Technology Roadmap for Semiconductors, this is a global roadmap that is published by a consortium of semiconductor companies, and it is meant to lay down the path forward. So it tells all other companies that in 5 years we need to be here in terms of device sizes, in terms of energy consumption, in terms of delay, and so on and so forth. And in those roadmap, this is a very important roadmap, similar statements started to appear, that we cannot build, the design of systems on a chip will resemble the creation of a large-scale communication network. Relaxing the 100% requirement of correctness may drastically reduce the cost. So this is actually a very radical statement to make for the semiconductor industry because we have always dealt with deterministic fabrics. The whole process, the stack, the compute stack from circuits up to logic, to architecture, to systems, it has always been built on a deterministic level of abstraction, right? So this is a very radical statement to make in ITRS. In 2010, there's an article in IEEE Spectrum, you can take a look at it. It also talks about how future computers, future computing platforms will need to manage errors. And this actually highlighted some of the work that came out of our group by that time. And now, zooming forward to today, you look at the major semiconductor research programs out there. They're huge programs. Each of these programs talks about a strong connection from systems to devices, right? So it's not about building good switches, great switches, giving it to the circuit designer who then builds great networks, who then gives it to the architect, who then builds wonderful architecture. We need the strong connection from systems, architecture to circuits to devices. So this is actually a big move from how research was done previously. And so JUMP, ERI, these are all more than $200 million programs that were launched in 2018. And in fact, I believe that it creates a wonderful opportunity for information theorists to really work with circuit designers and architects, because we have to manage statistics in the most efficient manner. And so Love and I have been sort of collaborating for quite some time on this topic, and we can attest to the benefits of such collaboration. And our collaboration started off in this center called the Systems on Nanoscale Information Fabrics. This was part of the StarNet program, which is a predecessor to JUMP. And in this particular center, we actually tried to bring the notion of Shannon and brain-inspired computing to the world of integrated circuits, to the world of architecture. And we, in fact, promoted this vertical integration from systems to architectures all the way down to devices. So we recently completed our 5-year tenure that ended in December last year. And the team that we put together, I think you'll recognize a few faces here. You see Love there. Some of the researchers here are from your community. So Greg Warnell, Andy Singer, we have Upmanyu Madho. I don't know if I'm missing anyone, and then we have a number of device researchers. And we actually got together and asked this question: how do we build computing systems of the future when our circuit and device fabrics are behaving stochastically, right? So it creates a real problem that we were working on. And so what did we really come out with? We had a portfolio of design techniques, design principles at the highest level. We translated those into architectures which were non-von Neumann architecture, but which were promoted and inspired by the notion of working with low signal-to-noise ratio. So instead of building reliable circuits, we say, let's build energy-efficient circuits, which may be unreliable, but then we employ statistical models of computation to compensate for errors, which is exactly the philosophy that's followed in the world of communications. You work with low SNR channels, and then you use sophisticated coding schemes to recover the reliability of that channel. And then we, of course, grounded our research in a number of prototypes. So Claude Shannon has been our inspiration from day one. I don't have to tell you his impact. You're quite aware of it. Complete theory of communications, A to Z. More importantly, the theory defines the architecture. In the world of computing, there is a theory, and then the world of architecture operates on its own. But here, you have a very strong connection between the theory and architecture, and that's very appealing. He provided fundamental limits on transmission rates. What is the best anyone can do? In the world of computing, these kind of limits are very hard to obtain because systems are very complex, very diverse. coding as a design principle to approach the limits. We want to know what sort of design principles we can come up with to approach the fundamental limits in the world of computing. So far Shannon ideas, though very appealing for computing folks, they've had limited impact in the world of computing. And this was not because of lack of trying. In fact, von Neumann in 1956, he wrote a paper in which he was addressing the problem of designing reliable Boolean networks when each gate in that network is allowed to make error with a probability epsilon. All right, so that's called the epsilon noisy gate model. And he had constructions that were talked about, that were presented. But right in the beginning of his paper, he says that the treatment of error that he took was not very satisfactory. In fact, he points to Shannon's work and says, if we can bring Shannon theory into the world of computing, that would be the way to do it. Winograd and Cohen had a monograph, Reliable Computation in the Presence of Noise. And this monograph was inspired by the thought, by the assumption that as you pack more and more devices into a chip, very hard to get all of them to be deterministic. Some of them will fail. If they fail, can I still build something reliable? But these sort of works didn't have much effect. Today when we build computers, when we build microprocessors, we don't use any of these techniques. Why? Because the construction is very complicated, very complex. There are other methods to get robustness. And so the good thing that happened out of that paper was a series of works that came out from the world of coding theory and information theory. So coding theorists and information theorists took that epsilon noisy gate model. It's a very compact model, very simple. And yes, you can play with it. One can come up with many different results. And so there was a series of papers after von Neumann's first paper that put bounds on when can a network be reliable, when can it be robust, given that the gates are allowed to make errors with a probability of epsilon. All right. Now, it turned out that all of those, if there were constructions, then they turned out to be very, very expensive. They turned out to be very complicated. So one would rather build a reliable gate than to have an unreliable gate and then use these constructions to make them complex. So it's not like the coding and information theorists have not come to this area. They have looked at this area, but we'll see why these kind of results, which are quite theoretically very solid, but in terms of practical impact, it didn't show up. Shannon capacity for logic gates, Peter Elias, he had this paper in IBM Journal in 1958, where he took again the epsilon noisy gate model, and he calculated the Shannon capacity of such a gate. And his conclusion was it is 0 for only for certain types of gates, one-to-one mapping, gates that do a one-to-one mapping, you may have a non-zero capacity but for the Boolean algebra, if you take the library of all possible 2-input gates, most of the gates have a capacity of 0. And Pulkit Grover in ISIT 14 also came to the same conclusion, right? And the reason for that is, I think Peter Elias clearly pointed out why it is like this. He said the formulation used for the problem is the problem. That is, the problem definition was so constrained that you get all of these negative results, that we define computing as the process of building Boolean networks. That's a very narrow and very small, kind of very focused way of looking at computing, right? The good thing about it is that the model is very simple and you can play with it. You can actually build up all sorts of theoretical foundations on it, but it's a heavily constrained problem definition. And then he goes further and says, it characterizes all of these results as sort of the pre-Shannon era results, similar to how communication systems were thought about prior to Shannon's work. A similar outcome we have in the world of computing. So Now there's another group of work that came out from the world of integrated circuits, folks like myself and my colleagues, who took very simple one-to-one mapping inverter. We said, let's take an inverter, which is the basic gate that you design in integrated circuits. Can we find its capacity? Can we find from the capacity, can we determine the minimum energy consumption of just one inverter? And so, you can actually get capacity numbers. You can actually get the energy consumption, minimum energy consumption in picojoules or nanojoules. So those type of works were done, but again, the question remained, what does it mean? How can I actually build systems that approach those limits? So the problem with all of this work, which tried to bring Shannon into the world of computing, was the focus on a gate level model, the epsilon noisy gate model. It has a number of other problems too. One, the gate model is unrealistic, meaning if you look at actual gates when they're built, if a noise pulse hits the input of a CMOS gate, you won't get an error. You'll get a dip. The output may respond to a noise pulse, but it'll recover. So CMOS gates are restoring gates. They don't switch completely. Latches, if you have a circuit in which you have a register or a latch, now that stores, that can remember, right? So those are the elements that make errors. So if you take a large circuit, you have few latches, few registers, most of them are gates. Most of those elements don't make hard errors. Hard errors are made by a small subset of it. So we can't focus on the gate level representation of computing, we have to move out, right? And so the alternative, what we need to do is zoom out and say, at the system level, how does computing look? What is a computing system trying to do? And let's address it directly, okay? Okay, so that brings me to the Shannon-inspired approach of computing, a systems-driven Shannon-inspired approach, where we look at the metrics with which we evaluate computing systems are different. The way we look at the problem of computing itself is different. So for example, instead of looking at a gate, we want to say that a function, this block has to compute a function of input data X, and the outputs are in error. Think of the outputs as observations. If I have the statistics of the error, the manner in which these errors occur, then looking at the observation and the statistical description of the errors, I can use techniques from estimation and detection theory to recover my output. Now, in computing, I'm restricted to low complexity estimator and detectors. That's a constraint, because we don't want to have the overhead of recovery to dominate, right? So, because all of these are on the same chip, and I could build the block C with very high reliability and with some energy consumption, and I want to beat that by orders of magnitude. And the way to do it would be to reduce, to make the block C statistical. Hopefully you get a lot of energy efficiency, and then throw in some additional building blocks to compensate for errors. So in the world of computing, the error recovery mechanism, the overhead of error recovery is also quite important. We cannot ignore it. In communications, to some extent, the energy consumption of the receiver is not as critical as the transmit power, right? Everything in communication systems is about reducing the transmit energy, because that's the big power-hungry block in a communication link. Here, it's not so. Here, we need both to be optimized. So it's a harder problem. Nevertheless, with Love, some of my colleagues, including Love, Naveen Verma, my students, Ameya Patil, we have, Love and I have a postdoctoral fellow, Yongjun Kim. We have this article that should be appearing soon in the proceedings of IEEE, where we propose a Shannon-inspired model of computing. And we start off by stating that design of computing systems should use information-based metrics, much as design of communication links have used these metrics. And furthermore, we have room for these different blocks. Encoding, there's room for encoding, there's room for decoding as usual, but also there's a huge body of work that can be brought in here in designing the channel itself. So in the world of computing, the problem is harder, but there's also a lot more flexibility, a lot more opportunities, because we can design all three components of this computing system: encoding, channel, and the decoder. And I want to give you a few examples of the channel itself, because right in that domain, in the circuit fabric domain, there are many different ways of trading off energy with statistics, with the statistical behavior of the circuit fabric. Okay. By the way, we are allowed to take questions back and forth, so feel free to stop me anytime. So once you have that framework in place, then it allows the designers to actually ask the question, how do I compensate for errors? Should I do encoding and then play with the channel, or play with all three, right? So of course the answer is you want to have the maximum degree of freedom, so you want to optimize across all three building blocks of this computing system. But it just turned out, the way we circuit designers think, we came out with a set of design principles in which one or two or more of these blocks are being optimized. So for example, today I'll share with you statistical error compensation, where you play with the error statistics of the low SNR fabric. You can tune it, engineer it so that the decoding becomes simple, right? So playing with the circuit fabric and the decoder is what SEC, or statistical error compensation, provides us. Professor Verma from Princeton, he has promoted the idea of data-driven hardware resilience, or DDHR, where the function that you realize in the low SNR fabric, that is adapted, that is modified in a data-driven manner, so that the output is, the mutual information between its output and the correct output is maximized, right? So that's another way of doing it. High-dimensional computing, it's actually very, it's similar to Shannon's random coding argument. That is, you take your input, project it into a high-dimensional space, and then apply an associative algebra in the high-dimensional space. So you're not trying to decode, you're trying to compute in an HD space, and then make decisions, right? So those are, and then the last one is Love's work, in which he uses Shannon limits to find out the optimal energy allocation for a Boolean network. So that's another example of sort of channel engineering type work, all right? So it depends on, it's a very rich framework for researchers to contribute to the design of these reliable systems, right? So it gives us lots of degrees of freedom. So with that, let me share with you some of the ways in which circuits can make errors, and what that energy delay and accuracy trade-off looks like for different circuit fabrics. So in circuits, there are roughly three categories of error sources. The first one is what we call as truly random sources, and examples being particle hits, device noise. Some of the emerging devices are intrinsically stochastic in nature. So RAM, I mentioned, Spintronics. Then there are practically random sources, which means they're not truly random, but because of the complexity of the design, you really can't model those effects very well. So you sort of back off and say, well, I'm going to model it statistically, all right? So I use the term practically random sources. The last one is sort of the aggressive, design styles that we employ. So when you build a reliable systems, typically in the world of computing systems, we put design margins, right? So I build a circuit. You told me that the circuit should operate at 1 gigahertz. Well, I'm probably going to design it at 1.5 gigahertz, right? And then provide it to you, and you'll take that and add another design margin on top and give it to somebody else. So at the end of the day, we have the design margining sort of builds up and adds a huge overhead. Now, in aggressive design styles, we say we don't want to do it. If you ask me for 1 gigahertz, I'll give you 1 gigahertz with the understanding that sometimes it's going to fail. And I will assume that you know how to fix it. You have techniques to fix it. So that's the sort of the third category of errors. Errors, why they can occur? Because you have reduced the design margins. So I mentioned in the beginning of the tutorial that in circuits we have this trade-off between energy and delay. And traditionally, when we teach circuits courses, when we build integrated circuits, we are sitting on this red line. That is, we try to make the behavior of the circuit fabric deterministic. Now, if we relax this constraint, then this red line becomes, you can actually move closer to the origin, which is where we want to be. But we want to be able to compensate for the stochasticity of the circuit fabric somehow. Right? So this is the picture that we have to keep in mind. No matter which circuit fabric we are dealing with, which devices we talk about, there's an intrinsic fundamental trade-off between energy, delay, and accuracy. Okay? And different circuits will provide that in different ways. All right. So let's take a look at truly random sources. This is particle hits, cosmic rays. You're dealing with nodes that are extremely small, and that store very small amounts of charge. Information is stored in terms of charge on capacitors, and they're very, very small. And whenever you get a particle hit, you get huge amounts of electron-hole pair generation. They get absorbed by those nodes, and they can disturb the charge that is stored on those nodes. All right? And this is truly random because you cannot predict where the particle will hit, how much charge carriers will be generated, and whether they'll be absorbed or not. So it's a totally random phenomenon. But there is the energy delay and error rate trade-off. So ED is energy delay and error rate. And you can show that a latch, this is a nice abstraction of a storage element, two inverters back to back. It's the simplest storage element. It appears everywhere. They have capacitances on these two nodes which store the charge, and if there's a particle hit nearby, then that charge can be disturbed, and the stored value can flip. Right? This is a positive feedback system. And so you can show that cosmic ray neutrons can generate roughly about 24 femtocoulombs charge on average, which is actually significantly more than the critical charge that is needed to flip the logic state of a latch. So it is very common. It's very easy to have situations where your chip is deterministic, works well, you take it into space or even on terrestrial ground, and you get bit flips and you cannot explain why that happened. And there are some news items you will see if you look back that pointed to cosmic rays as being the culprit. And there's a very clear energy delay accuracy trade-off, because one common technique to enhance robustness is just make the capacitances large. If the capacitance is large, C is large, then CV charge is also large, then maybe it can absorb those cosmic ray extra charges generated by the cosmic rays. But the moment you make C large, energy goes up because energy is proportional to CV squared. All right? So you can see a very clear trade-off between robustness and energy. And also you'll see that if you make C large, the circuit slows down. Right? So this trade-off is extremely clear in this particular example. Practical random sources. So you have a latch, a different sort of a latch here. It's called the true single-phase latch. And you have a supply voltage, typically 1 volt, ground, 0. But because it's part of a large circuit, the supply rails are not fixed. They don't stay steady. Right? Whenever a clock pulse comes in, the supply and ground, they start to shake. They start to wiggle. And if they wiggle at the wrong time, if they wiggle when a clock edge is coming in, after all, this is a synchronous system, then it's very easy for the output to capture an incorrect data. And so you can run a simulation, and it's very easy to create these scenarios where an error is generated, a logic error is generated. And once the logic error is generated, it is permanent, meaning it will then feed into the next block, which will have to process that incorrect logic value and then move forward. Right? So latches are the sort of the attractors. They are the receivers. In one way, they are sort of the receivers in a communication network, and they make errors. Right? Aggressive design style, I'll spend a little bit more time here. this is a technique called voltage overscaling. So we just saw if you, what is voltage overscaling? Let me just explain in the following way. Let's say you have a ripple carry adder, right? So you're taking two n-bit numbers, you're adding them up. The speed of that adder depends on how long it takes for the carry to propagate from the LSB, lowest significant bit, least significant bit, to the most significant bit, right? So if you add, take a binary addition, you'll see that you start from the LSB and then you propagate the carry to the MSB. So MSBs are always computed last, right? And the longer it takes to compute the MSB, the slower your ripple carry adder is going to be. So as circuit designers, we just tell you a number. We say this ripple carry adder will operate at 1 nanosecond, which means the MSB will take, in the worst case, 1 nanosecond to finish computation. Right? So we think worst case across all possible scenarios. Now, in voltage overscaling, we do the following. We say, instead of running the circuit in the worst case corner, I'm going to let it operate at some other clock frequency or some other voltage where I know that some of the MSBs will be wrong. Some of the MSBs will not have time to finish computation in the worst case. I know it, all right? But I will account for it in some other way. So most of the time, the adder is going to produce correct outputs, because most of the time it's, this is the path delay distribution. It's telling me, what are the different lengths of different paths in the entire circuit. Most of the paths are short. So most of the time, those are the paths that will get excited, and those are the paths that will determine the output. So most of the time, the adder is working fine. But once in a while, it's going to make an error. Today, when I design ripple carry adders, I look at the worst possible case. I take the most unlikely case, and I design for it. Here, this is sort of backing off and doing sort of a better than worst case design, right? Now, circuit designers don't want to do this because they want circuits to be deterministic. But if we have techniques to compensate for these errors, we would like to do it. And we do have techniques to compensate for the errors. In fact, you can take any of those arithmetic units and create this PMFs, error probability mass functions, as a function of the supply voltage. So the supply voltage is on this axis. As you reduce the supply voltage, the circuit slows down. And if you don't change the clock frequency, what you get are errors, high magnitude errors that start to appear. So if you take a slice of this 3D diagram, that gives you a error PMF at the output of the ripple carry adder at a specific supply voltage. So these characterizations you can demand from the circuit designers. Today, circuit designers are only going to work at that clock frequency at which the errors have probability 1, that the error magnitude is 0. We don't want errors. But if we back off from there and create a full characterization of the circuit fabric, then it gives the system designers a lot more flexibility and to come up with new design techniques for error compensation. All right. Okay. These are some of the measured error PMFs. They are not just in theory. So this is coming from a real chip that we designed. It shows you the error magnitude, probability of occurrence at a different supply voltage, a VDD of 0.4 volts. And then we can also simulate, the similar PMF can be obtained through hardware simulation. The point of this is that the lab results are very well correlated with simulation results, which is good news, because that means we can do lots of software-based characterization and then do design based on it and then fabricate the chip. All right. So these are available. These PMFs can be obtained. They can be measured or they can be simulated. And then we can use them as a form of channel characterization, channel characterized data for designing systems. All right. So it provides a basis for information theoretic analysis. Now, where is the energy delay error rate trade-off in voltage overscaling? It's very, very clear. Your energy comes from this relationship C VDD square. This is a digital circuit, CMOS circuit. So if I reduce the supply voltage, VDD, I can reduce energy consumption. But delay in CMOS circuits is inversely proportional to the supply voltage. All right, so as you reduce the supply voltage, the circuits slow down, right? And typically, if I want to avoid errors, I'll just run the circuit at a lower frequency. But in voltage overscaling, I don't do that. I run it at the same frequency and let the MSBs make errors. All right. So what sort of benefits can I get? Well, this is a plot of a 4-tap correlation filter in a particular process technology. You can see that as you reduce the supply voltage, your error rate starts to increase, but your energy also starts to go down. And you can predict that in this technology for that particular filter, you get about 9x energy savings if you can operate at an error rate of 60%, which means 60% of the outputs have at least 1 bit in error. This is the raw error rate, right? So can we actually compensate for that error rate effectively? That is, if I add some additional circuit blocks to compensate for it, I will lose this 9x. 9x will go down, but hopefully by not too much. And this is where the challenge is, right? We want these sort of curves, energy curves, to be very steep, and we want error rate curves to be very flat, ideally. And this is where channel engineering and circuit design comes in. This is how we, people like me, should be designing circuits so that we can provide these excellent trade-offs for system designers. Resistive RAM is similar. This is work of Professor Philip Wong from Stanford University. He's a device researcher, experimentalist, and he has experimental data characterizing the distribution of the resistances as a function of the programming pulse width and pulse amplitude. So RRAMs are these devices where you can convert it from one state, one crystalline state to amorphous state by applying the right level of right pulse width and the right pulse amplitude. And so this particular plot shows that based on where you are in the pulse width, pulse amplitude space, the probability of hitting the high resistance state will depend on it, right? So it's a probabilistic mechanism. This programming of RRAMs is a stochastic process. Spintronic, similarly, this is a joint work with Intel that brought this out. There is a very nice model for Spintronic device. This is a totally different device from RRAMs, where you use electronic spin to store the state of the device and therefore represent information. And in this kind of a device, there is a clear trade-off between energy, delay, and accuracy. So epsilon is your switching error rate. So here, this is actually an ideal epsilon noisy gate model that von Neumann had thought about proposed in his 1956 paper. I had said earlier that that model is not very realistic for CMOS, right, which is the mainstream technology today. But in spintronics, it's a perfect match, right? And not only that, we have a very nice characterization of the error rate, delay, and energy trade-offs. All right, so these models are there. It is available. One can, build up system theory ideas and then see how effective they are in practice. Right. So overall, the Nanofabric model, stochastic model that we have would have the input going in. There's an error-free output. Why not? And then there's some hardware errors, and there might be some approximation errors, estimation errors. Just to make it complete, we put in two sources of errors, one coming from all these random, truly random, practically random sources or aggressive design styles. So that's like one category. We put that, we denote it as eta. And I'm showing an additive model. This is just a simplification. All right, you can have more complex models if you want. And then we might be designing these circuit blocks to compute a function approximately. All right, so that creates another error, approximation error, that is denoted by E. And again, to summarize, we have this energy delay trade-off, And as we allow the circuit fabric to exhibit increased stochasticity, we start moving that curve towards the origin, which is where we want to be. We want to be there, but somehow we want to address the stochasticity of the circuit fabric. Okay. So that the next one is another example of a stochastic fabric which Love can actually share with you. This is a joint work between Love and Jean-Pierre Le Bertin. He's a device researcher at University of Illinois.
Yep, so I'll just quickly talk about a very interesting application in nanoscale computing, which is essentially one of in-sensor computing. So how can we sequence either the genome or the epigenome? And by genome, I think people know what that is, the DNA sequence. But what the epigenome is, it's further information that's encoded. This can be through methylation patterns that modify the bases. It can be histone codes, it can be other things. And these are actually quite important for cancer. Okay, and one thing to note is that this approach to sequencing is quite different than shotgun sequencing, which I think some information theorists are quite familiar with. Essentially, in these chemical processes, you take a sequence, you split it into pieces, short reads, and then you try to reassemble it like a jigsaw puzzle. And this is the classic work now of David Shea and his collaborators. But the way nanopore sequencing works is you take the full DNA sequence. It can be very long sequences. You take a small hole and you pass it through, and then you try to see how voltages or currents or other things change as you do that. And again, this has been recently analyzed for the case of biological nanopores by Wojtek Spankowski's group at Purdue, as well as Suhas Degavi and Sriram Kanan's group in UCLA and Washington. Okay, what we want to talk about today is actually, instead of using biological nanopores, can we use solid-state devices and use that for sequencing? And this is especially important for epigenomics and also for integrating into larger computing systems. It's not super obvious how you integrate a biological nanopore into a larger computing system, but if it's a graphene nanopore or a molybdenum disulfide nanopore, it's much easier to do. And further, there's signals that can measure, say, methylation patterns. Okay, so the basic idea of nanopore sensing with these solid-state devices is as shown in the animation. So you have your DNA sequence, it's going through the pore, and as it does go through the pore, there's a change in ionic current based on what is in the pore, and that creates the signal. So there's different characterizations of different bases, as well as methylation patterns and other things. And the interesting thing is that you can actually do what are called molecular dynamic simulations that actually give you a very nice characterization of what will happen. So you don't have to physically do these experiments in the lab, but you can use supercomputing to do these kinds of simulations, and they tell you largely what will happen. So that's ionic current. And the other thing that happens is that there's also a different kind of current. So in these solid-state devices, there's also current going across the sheet in which the nanopore is, and that also changes as the sequence passes through. And so since we're using electrically active materials like graphene or MOS2, that's a second signal that one can use to do this kind of base classification or epigenomic classification. Okay. And just to, again, like Naresh was describing, one can connect experimental work with the simulations and show that these models are actually quite good. So one can, this is work out of EPFL, Alexander Radinovic's group. And so they actually built these devices, and the molecular dynamics simulation predictions of ionic currents and sheet currents match up quite well to what they measured. And this also raises, again, very interesting engineering problems, which are perhaps not present in biological nanopore systems. So here, since we're building the nanopores, we can choose various factors like the diameter of the pore, the thickness of the material, the shape of the pore, whether it's a triangle or a circle or other shapes. as well the number of pores. In fact, you can do 2 layers and have it go through 2 pores. You can change the propagation speed, so how quickly does the DNA sequence pass through the pores. And this impacts the noise level in various ways. So thicker materials typically have less noise. Smaller pores allow less flopping around, and so on. Okay. And so now there's, one can define information theoretic limits to find the best parameter trade-offs among all these design parameters like the diameter, thickness, shape, number, and so on. And further, we can take matched filtering and other signal processing algorithms for decoding these currents and implement them directly in graphene or MOS2. And that's really nice because now we have a single device that does not just the physical sensing, but also the signal processing itself. And so we can get this to feed into the larger computing systems that we want to build. Okay, so I'll pass it back to Naresh to talk about some further circuit and system design principles.
All right, thank you, Love. So now we are shifting gears. Now we have some idea of how circuits might make errors. And we know that whenever we allow errors to occur at the circuit level, we usually should expect some benefits in terms of energy efficiency and delay, right? And so now the question is, how do we, at the system level, build systems that are reliable in spite of having these stochastic nanoscale devices? So there are 4 techniques, 4 topics that I want to go over to give you an illustration of the sort of design principles and design techniques we have come up with already to handle circuit level stochasticity in a very unconventional way. By unconventional, I mean not relying on traditional fault tolerance computing techniques. So fault tolerance, one mainstream technique in fault tolerance is replication. You just replicate the compute units and do a majority vote, right? That reminds you of repetition coding. Here, these are totally different compared to those conventional approaches. Okay. So I'll start with statistical error compensation. This is work that came out of my group. In statistical error compensation, it's very close to how we build communication receivers. So in this approach, we design a compute unit, block C, which is supposedly, let's say 90%, 95% of the total complexity of the system, and then we reserve maybe 5 to 10% in an estimator and detector that is then trying to compensate for that error. And because as a designer, I have control over the block C, I can engineer the error statistics as seen at the output. I can decide that the output y1, y2, yn, when they make errors, they make it in a certain way, right? And using that knowledge, I can minimize the complexity of the estimator and detector to get a very highly reliable output, right? So this is the high-level philosophy of statistical error compensation. So requirements, we want to minimize the cost of error compensation, and using SEC, we have shown that you can compensate for error rates up to 85%, right? Which means that you're allowing errors at the output of these computational units, 85% of the time. And we can compensate for it with a very low gate count, roughly 5 to 22%, maybe 25%. So unlike replication, where you have 200%, 300% overhead, right? Here you're talking about a very, very small additional number of gates that you have to put in. But energy savings, you can get about 40 to 70% energy savings in CMOS, right? So you're getting energy efficiency along with reliable output way beyond what is otherwise achievable. So what are the different types of statistical error compensation techniques? These are all different settings, different approaches to compensate for errors. Algorithmic noise tolerance is what I'll talk about in more detail. I'll do a deep dive on ANT. In stochastic sensor network on a chip, what we do is we design, it looks like replication, but in fact, if you take the original computational block, we actually split it up into smaller fractions. So the complexity of all of these, think of them as approximate versions of the original computation. And because they're approximate, they have approximation errors at the output. And on top, we make the circuit fabric stochastic. So you have hardware errors and you have kind of estimation or approximation errors. The eta and E, they appear at all of these outputs. But we have so many degrees of freedom that we can make the errors uncorrelated. We can make them independent if we want, and use very simple fusion techniques to recover the output. So this is stochastic sensor network on a chip. Soft modular redundancy, well, if you remove soft from the title, n modular redundancy replicates the computational units by a factor of n, and we do a majority vote. Here, instead of doing a majority vote, we do a soft voting. That is, we look at the statistics of the errors at the output of those n blocks, and then do some sort of a map rule. We find an efficient map rule to recover the output, right? And then likelihood processing is another approach to correct for errors. So let's take a deep dive into algorithmic noise tolerance. In algorithmic noise tolerance, we have a main block, which is what we want to implement. That's the function we would like to realize. And if you realized it in an error-free manner, the output would be y sub naught. Okay, y naught is our output. But because I've used voltage overscaling, or maybe it is implemented in Spintronics, or maybe I've used some other circuit technique, I'm letting some errors occur at the output, and those errors are denoted by eta. So what I see at the output of the main block is y sub a, which is the error-free output corrupted with some hardware errors. Now that is what I want to implement, but to compensate for errors, I'm adding all of these other blocks. The estimator is an approximate version of the original function, the function that generated y naught. An approximate version of that I implemented here. I don't allow the estimator to make hardware errors. So the estimator is making only one kind of error, which is estimation errors, E. Oops. So the estimation errors are E, and hardware errors are made by the main block, which is eta. The sources of those two errors are very different, and I have full control over the statistics of those errors, because I can use many different architectures for the main block. I can use different supply voltages, different circuit styles. So the statistics of eta can be modulated in whatever way I want. Estimation, there are many estimation techniques. I can use them to come out with different distributions of E. Now, if those, so it's very typical for us to see, for example, MSB errors at the output, and so that's the error PMF of eta, those black dots, and the one in blue is what is your estimation errors, right? So they're very different from each other, and because they're so disparate, the error detection is very simple. You take the two outputs, compare them. If it is greater than a threshold, then you claim there is an error, and you take the estimator output as the corrected output. Otherwise, you take the main block output, assume that the gap is small, the gap is there because of estimation errors, so the main block is probably not making any errors. So let's take its output, right? So it's very statistical in nature. You can analyze it. You can in fact show that this kind of an error compensation scheme is a highly approximate version of a map rule that looks at the two observations, y sub a, y sub e, and leverages the disparity in the error statistics to recover the data, right? So it's very simple, and you can show that the signal to noise ratio at the final output can be made very close to the error-free SNR, and that those two SNRs will be much higher than the SNR that you'll observe there and there. So the main block makes errors in one way, which brings down its signal to noise ratio. The estimator makes error in a different way, which also brings down its signal to noise ratio. But together, they have enough information at their output that we can recover the correct output. So this is the principle of algorithmic noise tolerance. I'm going to skip this one because it sort of just describes what I just said in more detail. You can define an event space for algorithmic noise tolerance, true positive, false positives. So this looks like a detection problem. the entire block at the output here can be viewed as a detector with inputs being y sub a, the output of the main block, and the output of the estimator. And given the distribution of eta and E, we can find the appropriate decision threshold and use that, and an optimal decision threshold can be obtained, and then we can use that in the detector to minimize the error rate, right? So a classical detection problem is what this has been, you can frame this as a classical detection problem and then solve it. But from a circuit side, just to remind you that these are not all given. We have control over this, and we can tune them so that overhead is minimized and energy efficiency is maximized. So this cannot be done in isolation. This sort of work needs a very close collaboration with system researchers and circuit researchers. This is a good example of it. You can do a very simplified signal-to-noise ratio analysis to show that the signal-to-noise ratio at the output here, these two, will be much worse than the SNR at the final output, which will still be worse than the error-free SNR, but the gap between them is much smaller. All right, so this is sort of the qualitative description of the signal-to-noise ratio that you will see when you analyze this system. Okay. All right. A number of techniques were proposed, prediction-based, reduced precision replica. So in all of these, the only thing that changes is the manner in which we are generating the estimated output, the estimator output. So in prediction-based technique, we are taking the output of the main block, and we are relying on sort of the temporal correlation in the output to predict the estimator output, right? But the detector remains the same. We are not changing the detector. In reduced precision replica, the estimator is a reduced precision version of the main block. And this is a very popular technique because you don't have to know anything about statistical estimation and detection. Circuit designers, architects, they can use it directly. If you have a 16-bit data path here, you replace that with an 8-bit or 4-bit and see what sort of results you get. So this has been a very commonly used technique. Input subsampled replica, you take the input. If the input is highly correlated, images, speech, downsample it, send it into a smaller block, and then do that detection. And then map, the classical technique of map. Okay, what is the overhead? So in all of this, let me go back here. Everything you see that is not in blue is the overhead. I want to keep that overhead as small as possible. All right. So this is always a question that comes up when we talk about error compensation. And it turns out that when you look at all of the techniques that I had shown you, the overhead ranges from about 5, I would push this number 22, depending on the technique, it can go up to 30%. All right. So that's a number that we have, our more recent designs have encountered, 30%. But you get these sort of energy savings, 3x to 6x. And more importantly, that overhead can handle an error rate of up to 60%, or previously I said 85%. So tens of percentages, error rates in tens of percent is really unheard of in the world of computing. Because in the world of computing, the techniques that are utilized are triple modular or n modular redundancy, or error detect and replay. You detect an error and then recompute. So it's like this automatic repeat request technique, which cannot handle very high error rates because the cost of error compensation is so high, right? Here there is no repeat request, there is no replay. We just do forward error correction, and we use the statistics of errors to compensate for it. This is a more recent work, July of 2016, signal processing transactions. It shows how the estimator itself can be embedded inside the main block. If you embed the estimator inside the main block, the overhead of the estimator, which was the red boxes I showed you earlier, that's gone completely. And that's the big overhead, right? Out of the 30%, 20% overhead, majority was the estimator overhead. So you can actually take it out completely by utilizing the properties of arithmetic units, and you can embed the estimator right inside the main block. And so this result, so today if we have to implement algorithmic noise tolerance, the only extra overhead we need to think about is the fusion block, the detector that I had shown earlier. So these are some of the chips that we have designed. So I talked about the theory of statistical error compensation. The first chip was implementing a prediction-based ANT. The second chip, this is actually joint work with Doug Jones, who is a signal processing faculty at Illinois. Yes, question? Yeah.
You said the final output Y from the ANT has a higher signal-noise ratio than Y naught.
Mm-hmm.
Is it high enough that?
It's not higher. It's not higher. I said it would be lower, but close to it. After error compensation, the Y naught, so let me go back a bit here. Yeah. So SNR naught is our error-free SNR. And after error compensation, the SNR at this output will be less than SNR naught because we are not doing perfect error compensation. It is statistical error compensation. So it will always be a little bit less.
Is it enough less that the architect then has to factor in the weaker signal-noise ratio when building these ANT blocks together? Does the statistical error handling propagate up the stack further past the systems level, or is it a small enough decrease?
Yeah. Yes. So that's a good question. The way to look at it, first of all, it's a small enough change, but I would view it in a different way. I would say that instead of comparing the SNR at the output with what we think as error-free SNR, we should be asking the question, what is the desired SNR? All right? So, error-free means that we have some notion of a deterministic function that is to be realized with some known data that goes. That's how computing systems have been thought of, right? So that's the error-free output, and compared to that, I'm getting some signal-to-noise ratio. But if you're doing, let's say, some inference application, right? So sensory data streams coming in, you want to make decisions, and let's say the decision is a classification, then the misclassification rate is what we are after. And so the recommendation here is let's go for that ultimate metric by which we will evaluate the systems and then build statistical error compensation to deliver that particular metric, right? So the only reason we use this SNR as just to show you that it's a non-trivial approach, just to let you know that, the two of them on their own can't do it, right? So that's the point, yeah. But yeah, you can always meet the required SNR at the output by appropriately, correcting for it. But feel free to stop me anytime. I'll jump. Yeah, so I was letting you know that all of these ideas have been vetted with real-life chips. They work very well. You can see accuracy of error rates of 86%, 58%. These are raw error rates. That's like your channel making errors at that rate, and then by correcting for those, we get an accuracy of these ranges, right? So it's really working very well, and you get energy savings, 20x here, 6x there. So you get energy efficiency, accuracy, while handling high error rate. So that's SEC, right? There's still a lot of work to be done because there's so many other estimation techniques, error compensation techniques that one can come up with, and those techniques may dictate how we build circuits. We have not done that, right? So if you come to me tomorrow with a very powerful technique and say, to realize that technique, we need error distributions to look in a certain way, then as a circuit designer, it gives me information to actually go back and think about a different way of designing my own circuits. So you're sort of giving some feedback for the circuit researchers, contributing to the design of circuits themselves. ECG classifier, the last chip I showed you there, just a summary of it. You can see that, so we have ECG signals going in, and we need to classify them as normal. It's a binary classifier, or abnormal. And so there is a algorithm called Pan-Tompkins algorithm. It's a very simple signal processing based algorithm. The architecture has a main processor, which is 11 bits, and the estimator is a 4-bit reduced precision version of the main processor. All right? And then the detector is sitting right there. That's the pipeline. You start with the low pass filter, high pass, and so on and so forth. And the final output is what we are measuring. And we are letting errors occur in all of these blocks, and then we correct for it in this ANT decision block. So you can show this is the accuracy, this is the detection accuracy and the raw error rate. If you did not compensate for errors, the detection accuracy drops down catastrophically. Why? Because you have MSB errors. When you get MSB errors, then it affects all the other blocks that follow it. And the slicer, the end slicer, is going to make an error. But with this technique, you can get up to 58% error rate. You can compensate for it. And then you see that waterfall curve of error compensation. It falls off the cliff after some point. So that's roughly 600x improvement in robustness measured. The graph on the left is a measured, lab measured data. You can build these chips, measure it, and report it. Right. Shannon-inspired Spintronics. This is a joint work with our collaborators from Intel, Sashi Manipatruni, Dmitry Nikonov, and Ian Young. And the student who worked on it was Ameya Patel. So here, we were asked to use statistical error compensation to work with stochastic spin devices. If you recall, I indicated that stochastic spin devices are efficient, more efficient than CMOS, but we don't know how to use it. Right? And if you make those devices deterministic, that is, if you run them slow enough with higher currents, then they consume more energy than CMOS. Right? So we want to be operating with these statistical stochastic devices, but produce reliable outputs. And so this is a simulation study, and it shows you here average error rate versus true positive rate on the y-axis. And the conventional system, once the error rates reach about 1 in 10 to the power minus 5, they start to roll off. Triple modular redundancy is the one in green. That is the conventional fault tolerance technique. Take 3 copies of the computation, do a majority vote. You get about 10x enhanced. You can handle maybe 10 to the power minus 4 average device error rate. But using statistical error compensation, you can go up to 100x beyond TMR or 1000x higher error rate compared to conventional. Right? So these are actually big numbers that show you the promise of these techniques. Now, in terms of energy, if you take 3MR, yes, 3MR is more reliable, but it consumes about 2.3x more energy because you're triplicating computation. With Shannon-inspired, not only you get that 1000x improvement, but you also get a 3x reduction in energy compared to conventional. We are still not quite beating CMOS. We still have not really crossed over. We have not yet beaten CMOS. Why? Because there may be better techniques than the ones we have chosen. Maybe there are better functions that we have to realize. So our goal is to get this red curve to come to beyond, to the left of the CMOS blue curve, and for sure, while maintaining its robustness. Right? So there's still work to be done. But this movement, moving in the opposite direction to 3MR itself was a great contribution, because it was thought, generally we thought that if you try to compensate for errors, you have to spend more energy. This shows no. If you do it right, if you do it the Shannon-inspired way, that's not true. Right? Okay, so there are a number of papers that have come out over the years. You can, take a look from concept all the way to ICs. I now want to spend a few minutes to talk about the other 2 techniques, which I don't know how much I'm doing on time. 8 minutes, okay, I should be done very quickly. So statistical error compensation, high dimensional computing, I mentioned. This is the work of Jan Rabai, Bruno Olshausen, who are from UC Berkeley, Shubhashish Mitra and Philip Wong, who come from the world of architecture and devices from Stanford University. They were all members of the Sonic Center that I indicated earlier. And their approach is to take the input and project it into a very high dimensional space, and then use an associative algebra to find patterns and to do all sorts of associative operations in high dimensional space. Now, this is very reminiscent, the first stage is very reminiscent of the random code, Shannon's random coding argument, right? When you go to high dimensional spaces, separability of features and decision making becomes easier. So this is what is being exploited. Now, to realize these kind of systems, you need a fabric, a circuit and device fabric that is massively parallel, extremely low cost, but highly unreliable, right? So this is sort of the property of the circuit fabric, device fabric we need. And they indeed have created this 3D vertically integrated device fabric in which they have layers of CMOS, RAM, carbon nanotubes that are stacked on top of each other that are all doing various sorts of functions. So you can implement multiplication, addition, permutations using these 3D stacking of these layers. So there's a device fabric, monolithic 3D integration that is sitting underneath, that is being used to implement this HD computing. And there's a paper that appeared in 2016 Low Power Symposium that describes how they are able to do language recognition using HD computing, right? Again, through simulation results. So you can take a look, and one question that always arises is, are there efficient efficient codes? So right now, this mapping is truly random, right? You take the input and then you project it into a higher dimensional space, randomly selected. But we know that there may be better ways of doing that projection, just like in, the codes are selected carefully, even though the even though random coding is a good proof argument, but in practice we actually want structured codes. Similar structured HD mapping codes might exist, we don't know yet. Data-driven hardware resilience, this is the work of Professor Naveen Verma mentioned earlier, in which he adapts the function that needs to be realized. So you want to realize the function f, but because of errors, you're going to get some different function. You sort of adapt the function to minimize that difference, right? So this is data-driven hardware resilience. And again, this is, there's a lot of, Naveen has a few experimental prototypes of these ideas that have been also proven in practice. And these are some of the papers where he has shown that you can take a feature extractor, which is, which is implemented on a stochastic fabric, and then you train the classifier to be aware not just of the data statistics, but also the errors that occur in the stochastic fabric. So the training process can be cognizant of both. And that way you can sort of chain the decision boundary and get the reliable outputs. Coding for serial buses. So in computing systems, in addition to memory, interconnect also dominates energy and latency. And so there are interconnect on chip, interconnect off chip. On chip interconnect is dominated by crosstalk. So the wires tend to be very tall and thin. If you bring them close to each other, then there's coupling capacitance between them, and that affects if two wires transition in the opposite direction, the delay becomes twice as large as if one of them were transitioning, right? So it's a big, huge impact on delay. And so a number of works, Srini Sridhara, a former student of mine, and a number of other researchers have come up with crosstalk avoidance codes. That is, how do you code the data so as to minimize the crosstalk between wires? This is a very different form of coding, different from compression and different from error control. Off-chip serial links, they have coding techniques that have been recently proposed. Amin Shokurolahi from your community had this paper in ISIT 16, 2016, and then Tejasvi Anand, one of the alums from our department. And both of them are looking at chip-to-chip communication, but coding to minimize inter-symbol interference. Right? So they actually do some time domain modulation of the transmit pulses so that the worst case ISI gets alleviated. So there's room here, there's a lot of interest in both of these domains to come up with new codes to minimize delay. Right? BR optimal ADCs. So now we are shifting gears and saying where else can we use Shannon theory? So A to D converters typically are designed so that they preserve the fidelity of the analog waveform. So you send me an analog waveform in, then the A to D designers use metrics such as effective number of bits. How many bits of resolution and linearity did I get when I created this A to D converter? In this work, this is a joint work with actually Andy Singer, Elise Rosenbaum, and Upmanyu Madho. Here, we are using a detection metric instead of a fidelity metric. So we say that the A to D converter is going to feed into an equalizer. It doesn't show here. But this output here should be an information preserving output because it will feed into a detector. And the detector is trying to decode the transmitted data. Under that constraint, what should be the A to D converter? How should it look like? It turns out this A to D converter is heavily nonlinear. Right? Typical A to D converters are designed to meet some linearity constraints. Here, we can be allowed to make it highly nonlinear, and you get tremendous savings in bit error rate. Even you go from 4-bit to 3-bit, a 3-bit BR optimal ADC gives you significantly more reduction in the bit error rate compared to uniform ADC. So this is also a practical design that was implemented in a prototype IC. Should I take a break here? Yeah, I want to actually take a break now, and this is the last part of this particular topic, error compensation techniques. But this is a sort of a very recent work, and I want you to be fresh with some coffee. So we'll take a break now, and we'll talk over the break in the meantime. So welcome back after a coffee break. So we were talking about how Moore's law has evolved over the years. And in the beginning of the tutorial, I mentioned that the von Neumann architecture has been the workhorse in the world of computing. Because it separates storage from computing, it kind of puts a limit on the energy efficiency and the latency of computing systems. And for data-centric workloads, that memory wall actually shows up in a big way. So recently, we have proposed an architecture which in fact is inspired by the Shannon theoretic way of looking at computing, which is called DIMA, Deep In-Memory Architecture, where we overcome this wall. So on this figure, you can see the traditional von Neumann architecture, storage, digital processor. Storage is typically analog process. That is when you read data, you read it on small voltages, you bring it out, bit line swings are small, you pass it through a sense amplifier, and then convert to digital, and then you send it into a digital processor. Right? This is how these systems are designed. And because this process of reading data is so well curated, because you have to make sure the bits are read correctly, this whole read access can be thought of as a high signal-to-noise ratio communication channel. So you have data going into the read part of it, there's some noise added, there's a sense amplifier that makes a decision, then the digital processor computes, there may be some approximation errors there, and then there's a slicer that generates the final decision. So this is how a conventional system works. There are at least two levels of decision in this path. One, the sense amplification, converting from analog to digital, and then the algorithmic operation of classification or slicing. In DIMA, we don't make any decision until the last stage, right? So how does DIMA work? In DIMA, we are doing all the computation. The read process itself is coupled to computation, and all of that is done in analog. So the moment you bring computing close to memory, you have to embrace analog nature of memory. And this is what deep in-memory architecture does. So here we read multiple rows at a time, unlike conventional memory where you read one row and then with very carefully you bring that one row out in the digital world. Here, we never bring out data into the digital domain. We always read functions of data and then compute functions of those functions until we get a final decision. So in deep in-memory architecture, we never read data, we compute and produce decisions. And because of this, there is no wall. That wall that you see here has been completely eliminated. There's always some residual digital sitting there, so you might do a few digital operations. The goal, the aspiration is to minimize it and bring it down to 0. To make this work, to make deep in-memory architectures work, we have to feel comfortable with low signal-to-noise ratio computation. And this is why traditionally these architectures nobody really thought about, because computing, digital computing, was viewed as a high SNR process. Here we are overcoming that because we know at the back of our minds that we have all of those error compensation techniques that we talked about just now. We can bring all of that to deep in-memory architectures if we so wish. So in deep in-memory architectures, energy efficiency is obtained through SNR budgeting, and accuracy is brought in by delaying the decision till the very end. We don't make any hard decisions until the statistics, until you capture the sufficient statistics and then you slice it. All right, so this is the principle of getting reliable outputs. And so there are a number of chips that have been produced in recent times. Earlier this year, Journal of Solid-State Circuits highlights 2 of our chips. The third chip currently, it was presented at ISIT 2018. This is a chip that Naveen Verma from Princeton had designed, and they are all different technologies, 65 nanometer, 130 nanometer. The more important part of this is the energy delay product reduction. So accuracy is the same as digital, but if you look at the EDP reduction, we are talking about orders of magnitude reduction. This is a big deal because just by modifying the architecture and doing things in low SNR, we are able to achieve these numbers. All right. So the first chip implements multiple inference kernels. So support vector machine is one example, template matching. The second one implements a random forest classifier. The third one uses on-chip training to compensate for analog non-idealities. And the last one that implements an ADA boost algorithm, classification algorithm. So these are all machine learning kernels being realized in silicon, but being realized in a non-digital fashion, in a deep in-memory fashion. And that's how it gets its energy efficiency benefits. There's an article that was published in March this year where it highlights the chip that Sujan, my student, designed, and that was presented at ISSCC. You can take a look. And so this is actually attracting a lot of attention in the circuits community. There are special sessions being organized to learn more about deep in-memory architecture. In fact, right after this conference, I'm going to the VLSI symposium where I'll be talking about this topic, deep in-memory architectures for machine learning in silicon. So just to remind all of us that theoretical ideas, to have them have an impact in the world of circuits, we need to bring them down into silicon or beyond CMOS. So hardware demonstrations, chip demonstrations are very important. And through the Sonic Center, Sonic researchers have demonstrated that multiple number of times over the 5-year duration of the center, both in CMOS and also in beyond CMOS. So at the end, this is a big high-level picture of what we want to accomplish. This is a figure that our collaborators from Intel suggested, that traditionally we've been optimizing energy through scaling and through better architectures, handling complexity issues. But if we bring in Shannon-inspired concepts, then it gives us a third axis into scaling, which is to bring in device error rate. not relying on devices to be deterministic, but to let devices exhibit, nanoscale devices exhibit error rates, and then compensating it for using Shannon-inspired approaches. So there is a big, very important role for information coding theorists to come into this world of semiconductors and make a contribution. We need you, right? So with that, I'm going to hand over to Love, who will walk us through the rest of the tutorial.
Great, thanks Naresh. So I'll talk through several vignettes of key statistical information processing problems, many of them that Naresh has already discussed, but now trying to ask, can we take Shannon theoretic approaches to understand fundamental limits, prove theorems, develop optimal design principles, and so on. And then at the end, we'll talk briefly about some open problems and conclusions. Okay, so let me again go back in history a little bit to this very classic book by William Pierce from 1965. And what he argued was that what every engineer needs is a good set of limit theorems. And I think most of us agree as information theorists. But I think circuit designers are starting to understand this as well, that theory can actually inform system design. In particular, for systems on nanoscale information fabrics. And there's several reasons that I think circuit designers and systems designers are starting to appreciate. That fundamental limits allow us to get benchmarks that allow us to evaluate new technologies on an absolute scale, rather than only comparing to previous technologies. Not just saying that it's 100x better than the previous thing that was done, but in fact within 0.0001 of what can be done. And so it's a more fundamental scale. Another aspect of fundamental limits is it gives us ideals for pushing industry and researchers to build technologies that approach or achieve these limits. So if we know what the best possible thing is, maybe we can work hard to actually go towards that. Third is it establishes the playing field in terms of which resources and performance criteria are actually fundamental and which are largely unimportant. So certain aspects of circuit design, certain resources are actually perhaps largely irrelevant and we don't need to care about them. We only need to care about the fundamental dimensions. And then finally, in delineating what's possible from what's impossible, we can get some insights in how to operate at that boundary, this boundary of optimality. That is to say, we can get design principles for system design. Okay. And as Naresh has mentioned, one of the key inspirations for this line of investigation is in communications. And as we know, coding theory has been largely set up as this quest for Shannon capacity. Over the 60-year history or 65-year history, there's been growing interest in just marching towards capacity, taking the road to capacity. And once one was able to get within some fraction of the Shannon limit, that was considered a very kind of classical achievement and something that we can now perhaps stop. Right? But on the other hand, in semiconductor scaling, there's been, again, a march, an ideal of performance, but the lower limit has been zero. Right? The goal has been zero energy consumption and zero volume and so on. It's not clear what the lower boundary is here. And that's something that if we can develop theorems, will actually help the field quite considerably. Right? Once we know what the fundamental limits are, we know what we can aim for and what we cannot aim for, and then stop there. But also develop maybe other ways of approaching the problem. Right, so as we know as engineering theorists, there's been a long history of these kinds of fundamental limit theorems, whether it's Carnot establishing fundamental limits on the efficiency of engines, or Shannon establishing fundamental limits on communication, or more recently, Karaman and Frisoli establishing how quickly you can fly through a forest without crashing. So this is the style of thing we want to do, but there's one key aspect of this that I want to emphasize. Is that one aspect of proving fundamental limit theorems is actually designing a closed deductive system in the first place. Bruno Latour is a sociologist of science, and in describing Carnot's work, what he said was, Carnot's know-how is not about building a machine, but rather a diagram. This diagram is drawn in such a way that it allows one to move from one engine to any other, and indeed to non-existent engines simply drawn on paper. Real three-dimensional steam engines are interesting, but localized and cumbersome. Right? This emphasizes the point that if we can draw a diagram of an engine or of a computing system, then we can prove these limit theorems and really understand kind of fundamental properties of them. Okay. Likewise with Shannon Capacity. Again, he defined a closed deductive system that communication is this diagram. He, for example, excluded the notion of semantic aspects of communication in defining the technical problem. Okay. And so again, we want to do something similar. We want to move from what Galileo called machines in the concrete to machines in the abstract, restricting attention to, say, a block diagram, where there's attention placed only on fundamental physical resources like time, energy, or volume, and fundamental performance metrics, some notion of reliable computation rate, and ignoring perhaps other things. Okay. And as Naresh had introduced, one block diagram that we've come up with for these nanoscale computing fabrics is as follows. So there's an input X, there's an encoder, there's some notion in our heads of error-free computation, which is corrupted by noise. But in fact, this is kind of a single block, and then there's perhaps some decoding. Right? And here, unlike in communications, we don't have X hat at the output, we have Y hat, which is meant to be the reliable estimate of Y naught, the error-free computation. Okay. One can also think about this in perhaps a little more Shannon theoretic way, where you have the traditional Shannon diagram of communications. So here we think of the input to the system as again in the same way. We have an encoder or a transmitter, noise, and then the receiver we can think of as a computing device, which is corrupted by noise, and then finally a destination. And this kind of redrawing also emphasizes the fact that the decoder might be a computational unit, and that might be corrupted by noise itself. That can't be just incorporated into channel noise. Encoder noise in general can be just thought of as part of this kind of computation noise. Okay. And again, to re-emphasize what Naresh was saying, the current approach, the current approach in the semiconductor industry is very much let's build a good device and use that to build a good circuit or a good architecture, and then use that to build a good system. But with the end of Dennard scaling and Moore's law, in fact, even the semiconductor industry has changed the name of the roadmap. So it used to be called the Roadmap for Semiconductors. Now it's being called the International Roadmap for Devices and Systems. So right in the name, it says that we need to emphasize the device physics and kind of understand their properties and how they play in at the systems level. Okay. So we want to try to understand these new device technologies like spintronics, carbon nanotubes, graphene, nanoscale CMOS, and so on, and new focus on these system theoretic approaches to deal with noise. Okay, so we want to change how the semiconductor industry works in some sense, which is perhaps a very difficult thing. Right? Culture change is perhaps the hardest thing to do. But what we hope to do is that we want to take devices and take their stochastic characterizations directly into systems theories along the lines of information theory, and then use those to drive optimal design principles. Okay, so we want to go from devices, so physical models, to systems theory, and then back to system design principles. And then also going from systems theory back to desirable properties of devices. Right? So we want to understand which kind of devices are actually the things that will give us the most impact at the systems level. Right? So we can tell device physicists maybe pursue these kinds of goals. Okay, so this is the kind of Shannon-inspired approach that we want to pursue. Okay, and of course, as every engineer needs a good set of limit theorems, we also want to establish what the Holy Grail is. Okay, so that's kind of where we want to go. Okay, and as I want to go through several kind of vignettes of these kinds of limit theorems and design principles that seem to emerge. So one is on fundamental energy limits for basic designs like algorithmic noise tolerance. Another is information theoretic limits for phase change memory, limits of constructing reliable memories from unreliable components, where we fundamentally take circuit complexity into account. So that overhead that Naresh talked about is part of the theorem itself. Talking about energy reliability limits in Boolean circuits, as well as deep neural networks. And the key difference between kind of classical work by Pippinger, Hayek, Evans, Schulman, and so on, is that energy is built in here. So we're not just counting the number of Boolean gates, but in fact, we can optimize their properties by allocating energy. And finally, I'll talk briefly about limits of defect tolerance in faulty computing hardware. These are permanent defects rather than transient errors of the type that we're discussing in the other segments. Okay. There's also a variety of other techniques that have emerged, including coded computation, which I won't mention so much here. There was a tutorial at ISIT last year, in fact, fully focused on coded computation. Okay, so Naresh mentioned there's a bunch of statistical error compensation techniques. Extensions of modular redundancy, interwoven redundant logic, which goes back to quadded logic by Tryon, algorithmic noise tolerance, which I'll focus on here. And the basic question here is what can be done for these particular strategies that resemble repetition in one case, or ARQ, or forward error correction. Right? So can we do kind of a communication theory style analysis? And the basic idea we want to do is we want to model these computational structures as multi-terminal source coding problems. Right? So what we want to do is, for example, think of the ANT structure, the algorithmic noise tolerance structure, as a CEO problem from multi-terminal source coding theory. So we'll think of these, the main block and the estimator block, as two observations of a noiseless computation S, where Z1 and Z2 are these two perhaps independent noise sources, perhaps there's some relationship. And then the decision variable is treated as a reconstruction block. And so we're going to think now in terms of a sequence of problems. And we'll think of these blocks as vector quantizers and with a reconstruction. And we'll think about the complexity of this fusion block in terms of the sum rate, in terms of kind of the digital complexity. Okay, and that's the analogy we want to make. And of course, there's some looseness in this analogy, but the hope is that there will still be design insights emerging from it. Okay, so as we all know, there's an exact characterization of the rate distortion region for the Gaussian CEO problem. This was established about 15 years ago now. And so what we want to do, and this was under mean squared error criterion. And so one can prove a very easy theorem that under mean squared error, any algorithmic noise tolerance system is only better than a Gaussian CEO problem. And that's because Gaussian noise is the worst case noise. Okay, so this gives us a bound. So the Gaussian CEO problem has a rate region. ANT in this modeling approach will only be better. And so we can use the Gaussian CEO problem as a way to get some insight. Right. Furthermore, we can convert from mean squared error to a more useful performance metric for AI and machine learning applications, which is logarithmic error. And there's an entropy power transformation. So in the Gaussian case, in fact, one can prove there's a one-to-one mapping between mean squared error and logarithmic loss. And so one can convert the rate regions by doing some substitutions. Okay. And so again, now we can use the Gaussian case as worst case for any of the algorithmic noise tolerance noises we might observe. Okay. And so now we have kind of this idea that we have an analogy between the ANT system and the CEO problem. And so now we can argue that the fundamental limits of circuit reliability, the error in performance, is governed by circuit complexity parameters, which were modeled through these rates. And one of the key insights that emerges from this analogy now is that for any of these branched architectures, whether algorithmic noise tolerance or other ones, the best way to improve performance is actually error engineering. And the reason this happens is because in the CEO problem, what has been shown is that there's different scaling laws of distortion with respect to rate, depending on the observation noise. So if you go back to the work of Toby Berger, whether you consider Gaussian noise or discrete noise, it's fundamentally different how the distortion scales with the complexity, and likewise with bounded noise. Right? And so you want to really move in this direction if you can. You want to engineer the noise so it's more and more discrete. And that's the high-level design principle that emerges from this analogy, that we want to engineer the noise, which we can because it's a circuit we're designing, to be more and more discrete if we can. And that's what will give us the biggest gains. And in fact, Naresh and his student Ameya have been able to do this. So they've been able to take noise that was basically a continuous noise and engineer it such that it's very much discrete. And this, by the insight from the rate distortion theory, tells us will perform much better than it would otherwise. So you get kind of the pithy insight, engineer your noise so it's discrete from the information theoretic principles, and then you can go ahead and actually do this with circuit design techniques. Okay. All right, so now let me go to another vignette, which is storing analog information in these emerging phase change memory systems. And so here, again, we want to make use of the physical properties of the channel as much as we can. Right? These are these analog systems. And in fact, we also want to use the statistical properties of the source, like images, for example. Okay, and this is work of Bruno Olshausen, Philip Wong, and others, Jesse Engel as well. Right, so we're going to think of the memory system, whether it's phase change memory or RAM or these other emerging devices, as a noisy channel, as usual. And of course, as we know from information theory, very classical work going back to Shannon, it's the conditional distribution, the forward test channel, that determines the capacity. I'm sorry, the backwards test channel. And so that's how we want to do the optimization. We want to try to use the capacity achieving input distribution as much as we can. Okay. And as is well known, we want to find these capacity achieving input distributions, and in nearly any case that you can think of other than Gaussian cases with finite support, the optimal input distribution is continuous. Okay, so contrary to the traditional approach in circuit design, which is to use a finite constellation, a discrete constellation, we specifically want to use an analog signaling scheme. And again, that just emerges from classical work on capacity achieving input distributions. Okay? The discreteness only happens in very special cases. Okay? Okay? And so we can go ahead and do that. We can actually use the experimentally measured noise properties to get the optimal right distributions. And then putting that all together, we can also try to use the properties of the source and get an optimal joint source channel coding scheme. And by doing that, we can improve the performance quite considerably over naive schemes that circuit designers might have used otherwise. Okay, so we can improve the SNR quite considerably by using joint source channel coding. One of the difficulties with joint source channel coding, though, is that characterizing the sources is not so easy. Right? If we're looking at natural images, they have very kind of complicated statistics. And in fact, even the phase change memories that we were just showing you, these distributions, they were experimentally measured in the lab, right? It's not very kind of closed form expressions for these. Okay, so what we actually, what Bruno and his team have shown is that you can actually use autoencoders to do the joint source channel coding. So actually draw on neural networks to learn the statistics of the joint statistics of the source and the channel. And now, since it's an autoencoder, you're going down to this lower dimensional space. You start with an image. So the encoder part of the neural network and the decoder part of the neural network, you can actually take advantage of directly in a Shannon theoretic framework. And you can design the encoder and decoder parts of the neural network to minimize mean squared error or other performance criteria that you care about. Okay. So again, just to emphasize this point, so we're taking raw natural images. We're taking the physical properties of, say, phase change memory. We're designing these neural networks to match them together. And what you get is something like this. So here it's a fairly large, so there's 28 by 28 pixels. So how much is that? Like 800 pixels, something like that, right? And we're storing it only in 40 single devices. Okay, so it's compressing it a lot. And yet, when you recover, you can make out the numbers quite well. Okay. Or if you look at images, so here Yeah, it's 0.1 devices per pixel, so reducing the number of analog pieces quite considerably. You can, again, get quite a good representation of the bird in this case with this joint source channel coding. And again, this is kind of different than what circuit designers would do otherwise. There's no notion of information rate here, right? We're matching the physical properties of the physical device with the natural statistics of the image of the source and doing that directly. And so this is quite reminiscent of, say, Michael Gaspar's work on measure matching in joint source channel coding as well. Right? So you try to see, can I get this autoencoder now to match things together rather than things being naturally matched themselves. Okay. Also works for dog images in case you care to know. Okay, so the key insights again are that emerging memory devices are intrinsically analog, these phase change memories, RAM, and so on, and they can be used to store analog data directly. And the fundamental limits are drawn from these capacity achieving input distributions and the channel noise properties. Right? And so this limit can be realized if we do adaptive joint source channel coding, perhaps using neural networks. And this style of thinking is actually also quite relevant for other kinds of deep in-memory architectures or compute memory, as some call it. Just some work that's about to appear in the Transactions on Communications, I believe, from Lara Dolacek's group at UCLA, is doing this kind of matching for computing the Hamming distance for k-nearest neighbor classification. Right? Or in fact, computing Hamming distance is kind of central to all kinds of algorithms, right? How close are two things? So again, they're able to kind of take the statistical properties of the RAM or the phase change memory and use them directly in kind of a coding scheme. Okay, so this is kind of nice, right? This is very classical information theory, but it's actually becoming relevant now with these new physical devices. Okay. On the other hand, we can also think about this very central question: can we think about memory storage forever? So how do we store information in a system constructed from unreliable components? So everything is unreliable. The storage elements are unreliable, the circuits are unreliable, nothing is reliable. But we want to store things forever. And we want to essentially construct this reliable memory system. And here we want to explicitly take circuit complexity into account, this notion of overhead. If you look at traditional information theory, no one really counts how many gates are in your encoder or how many gates are in your decoder, how much energy your encoder uses or how much your energy your decoder uses. Here we want to make that a fundamental performance criteria itself. Okay, it's, I would argue, a good stylized problem for understanding information processing in unreliable nanoscale fabrics in general. Right? Storage and retrieval is key to most any computation. Okay. And this is work that goes back to Michael Taylor in the 1960s and also Kuznetsov. And in fact, Taylor was a student at MIT. He had a pretty illustrious doctoral committee. Right, so Bob Fano, Bob Gallagher, Claude Shannon, and Peter Elias. So pretty much if you needed to know something about computing or communications or coding theory, these were the guys to talk to. Okay, so what Taylor did in 1968 was a constructive architecture for these kinds of memory systems. So what he said is, let me take a bank of registers. These are noisy. I'll be able to put things in, I'll be able to put things out. But the key part is that what I'll actually store here is a code word from a low density parity check code, an LDPC code. And once in a while, I'll take what's in the registers, send them through a decoding circuit, which itself is constructed from noisy logic gates, and put it back in. And I'll keep doing this. I'll keep refreshing this once in a while. And whenever I want to look at what's in here, I want it to be within a decoding region of the code. So the information is preserved reliably forever. Okay, if I can do that, yeah. Yeah, that's right. So since Gallagher was one of his advisors, it was, yeah, 1960, 61 was Gallagher's work, and then this is just a little bit after that. Yep, and this was published in the Bell System Technical Journal in 1968, I believe. Okay, so the question though is, can I actually achieve all that I just described? Can I store things reliably forever? Can I use only a linear number of gates plus registers in the number of information bits and so on? Right? This would be easy if I could just make this arbitrarily complex. Right? I just do n modular redundancy, but n going to infinity or something, right? So that's what I want to do is keep this overhead as a linear fraction of the information rate. And what Taylor showed was this constructive architecture actually is effective. It does what we need to. I'll go back and define things formally. And with only a linear increase. So, so let me, I'll come back to the formal definition in a minute. But let me also just mention this idea of a noisy decoder architecture has actually now become a fairly standard topic of study in information theory and coding theory. We want to ask maybe just for the communication problem, is it possible to communicate reliably when the device used to correct channel errors makes errors itself? Right? That seems kind of tough, right? You might assert a folk theorem that says this is false. Right? If the thing at the end is making errors, how can you expect it to be reliable? Okay, but what one can show, for example, I showed in my doctoral work, is that this is indeed possible. You can communicate at Shannon reliability, arbitrarily small error probability, even though the decoder itself is making errors. And one can also analyze very specific constructions like the Gallagher A decoder, but with noisy circuits, Gallagher B decoder with noisy circuits, and so on. You can also use expander graph constructions and even extend this basic idea to general belief propagation systems. So there's been a lot of work by Bane Vasic, Lara Dolacek. There's quite a few other people in various places that have worked on this. Okay. And now we've been able to use modern ideas from coding theory, like density evolution, expander graphs, and so on, to be able to do this analysis, which were unavailable in Taylor's time. The code optimization approaches as well. Okay. One other idea one might think about is now that we can analyze general belief propagation systems when they're implemented in noisy circuits, does that say anything about biology? So belief propagation is often thought of as the way that the brain itself works. And one of the things that often happens in neurodegenerative disease, like Alzheimer's or Parkinson's, is there's kind of a phase transition. So things are working pretty well, and then there's a drop-off. So there's a phase transition exactly like a decoding threshold in these coding systems. Right? So one might wonder, can we actually take these ideas that perhaps started in theoretical neuroscience back to theoretical neuroscience? Yeah, just as an aside, let me just briefly tell you about one of the greatest experiments ever done. So this is done during the war. This researcher in Britain. So what he did was he took human telegraph operators, right? So they're listening to Morse code and writing down what they hear. Okay, so very much a decoding problem, right? And notice that they're not wearing any shirts. The reason is because they're being put under heat stress. So they're raising the temperature at which they're operating. So a lot of the kind of competent operators, their error rates start falling precipitously around 95 degrees Fahrenheit. Good operators, it's more like 100, and then exceptionally skilled operators, you don't see their phase transition until past 105 degrees. Okay, so this is kind of neat, right? This is the average error probability in decoding Morse code. So this is exactly the phenomenon I was just describing. There's a phase transition. Better codes or better decoding circuits seem to have a higher phase transition. Okay? And this is quite a bit like this neurodegenerative process. Okay, so anyway, back to circuit design. Interestingly, there's also observations now that circuit noise can even enhance message passing decoders. They can actually work better than they would otherwise, than the noiseless versions. So the basic idea is that a little bit of noise can actually push you out of local minima. So these algorithms often get stuck, but just a little bit will push you out of, say, stopping sets or other combinatorial structures that get you stuck. This was first seen in our work on associative memory using these coding theory ideas, but now it's been seen by several groups by de Klerk and Savin, Bane Vasic, and others. And kind of the theory behind it is related to stochastic resonance and convexification of energy surfaces. A little bit of noise actually smooths things out. That helps you get unstuck. Okay, and which is described further in this proceedings of the IEEE paper. Okay, so again, this is kind of an interesting phenomena that we're starting to see, is that noise is not just something to fight against, but noise, a little bit of noise can actually help you. Even in terms of wiring errors, a little bit of noise can even help you there. So if you have a miswired circuit, sometimes it can do a little bit better than if you had a correctly wired circuit. So structural noise can even help. Okay. So one specific example is this associative memory model. And so this is kind of a structured code, very much LDPC-like. And this was designed for memorizing patterns with strong local correlation and linear constraints within the clusters, which matches natural stimuli like dogs and pigeons, and also matches cortical column structure. And what we were able to prove is that a neural network with internal noise, this within decoder noise, outperforms one without while maintaining the same capacity. Okay, so that's the style of result that you're able to prove on this noise enhancement effect. Okay, but now coming back to Taylor's problem. So how many extra noisy circuit components are needed to reliably accomplish a task like information storage as compared to the number of noiseless components that can accomplish that task? Okay, so we'll formally define circuit complexity. So we have an elementary operation as the Boolean function of two binary operands. An alpha noisy logic gate is correct with probability alpha. Alpha noisy register stores things correctly with probability 1 minus alpha. And we think of a system as built from these components, either noisy logic gates or noisy registers. And the complexity chi is the number of components within the system. Okay. So for example, this is a triple modular redundancy system. It has 3 registers, 5 logic gates. It implements 3 input majority. So it has a redundancy of 8. So you could have done this with 1. Now you're going to have to do it with 8. And if the registers and gates are noiseless, then the error probability, if the registers are noisy, but the gates are noiseless, then the error probability is this quantity 3 epsilon squared minus 2 epsilon cubed, which is not arbitrarily small. Okay, so what we want to do here is count how many extra gates we're using, but be able to achieve not this small number error, but arbitrarily small error. Okay, so that's what we're aiming for. So we want to define reliability as follows. So we're going to be storing k information bits. And so we'll say that the system has storage capability of k. And we'll consider a sequence of memories. So we'll consider it increasing in size, ordered by this storage capability I. And we'll say that the system is stable in this sense of recovery if it satisfies the following properties. It has a rate. So for any k and m sub k, it has to have 2 to the k allowed inputs. Right, so that's the code book. We have a class of states associated with each input, and these are disjoint. So these are disjoint decoding regions. The complexity must be bounded by theta k, where the redundancy, that should be a theta, is fixed for all k. So we only want a linear increase in overhead. And then the main property that we let lambda be the probability that the state is not in the correct decoding region at time t. And we'll look at the maximum error over all such decoding regions. We want that probability to be less than delta for arbitrarily small delta for any time into the future. Okay, so if we can do that, so we want the memory to stay within the decoding regions forever. You can wander around a little bit within your decoding region, but you have to stay within your decoding region forever. Okay, that's the notion of reliability. And now the storage capacity is defined as the inverse of the redundancy, so 1 over theta. Okay, and again, notice now we're counting not just the registers, the memory storage elements, but we're normalizing also by the number of logic gates. Okay, so we're taking circuit complexity fundamentally into account in this formulation. Okay, so the overhead is built into the definition. So now it's not number of information bits per channel usage, but number of information bits per storage element plus logic gate. So you're normalizing by everything that's in the system. Okay, and the goal is to determine the fundamental limits on the storage capacity. Hopefully it's close to 1, but it'll be a function of the noise. It has to be between 0 and 1. Okay, and what Taylor's work and work that I did and others have done have been constructive architectures, and you can compute how well they do. But what's been lacking is lower bounds. Right? So how do you think about lower bounding something like this? And that's not so obvious. Okay? So these achievability schemes are, the achievability schemes give lower bounds on the capacity. So Taylor showed it's positive, and for example, I proved that you can find very specific constructions and compute these upper bounds. Okay? And you can optimize degree distributions using techniques from coding theory. Okay? And in particular, you have to actually count how many gates things take. So you have to count how much the Gallagher A correcting network, when it's implemented with a minimal realization, how many gates it actually takes. So how much does it take to do a majority? How much does it take to do a parity check, and so on. Okay, so that's where you get those numbers, and those translate into circuit degrees and so on. Okay, so you can do this count, and that's where that 1/34 number comes from, just counting how many gates there are for a given degree distribution. Okay, and then you get this number from the decoding threshold. Okay, right, so how can we get kind of upper bounds on this capacity, converse arguments that are tighter than definitional bounds? And this, again, as I was saying, is not so obvious. So how do we do this? Yeah. So one easy way to do it is just not count the logic gates, right? So then we can just use Shannon's converse argument. Right now it's just a standard communication problem, and that allows us to get some bound. So again, for that same example that I've been using, for the achievability part, we get a converse part that's less than 1. So it's a non-trivial bound, but perhaps not so good. And again, this just follows from Shannon's capacity result of the converse part. Okay, but this seems like we're not doing anything useful, right? We didn't count how many logic gates there were. So one can take the circuit complexity of the correcting network into account when we do this. And now we need to think about how much entropy is generated by the register noise and how much of it needs to be dissipated to maintain stability. Right, so we think of the code words kind of being perturbed, and then we dissipate it, perturbed and dissipated. And the question is, how do we balance those things such that we can achieve the notion of stability? Right, so that's this, right? So we store something in a decoding region. It gets perturbed by noise in time step 1. We do some noisy correcting, which tries to push it back here. In time step 2, gets perturbed in time step 3, try to correct it, and so on. So that's how we think about it. And the question is, how can we ensure that it stays within this region? So the noise is generating some amount of entropy. We're dissipating some amount of entropy with our noisy logic circuit, and so on. And so the thing that we want to see is we think of the entropy as a state variable for the dynamic evolution of the memory. And by Fano's inequality, this will imply properties of the error probability. Okay, so that's the basic idea that we can use to get a better converse. And notice that we actually don't need to dissipate the full amount of uncertainty that's generated by the noise. We only need to stay within the decoding region. Like you can imagine an approach where it goes up, we go only back part way, then it goes out, and we only go back part way. And so that's another question. Does that help us in any way? Right, so what one can show is that that doesn't help us. So it is necessary for the correcting network to dissipate all of the generated entropy at each time step. Otherwise, there would be increases in entropy over each time step interval. And the basic argument is that a biased random walk would otherwise almost surely leave the decoding region at some finite time and thereby violate the stability condition. We could also make the regions larger using a rate less, code with a rate less than capacity, but then the same result still applies. Or we could also consider a correcting network that dissipates less entropy than produced. And although the time of the exit from the decoding region is delayed, the random walk will still almost surely leave the decoding region. So none of these kind of tricks will help. So we do need to specifically characterize how much entropy is generated by the noise and how much entropy can we dissipate with this noisy logic network. Okay, and we need to consider for this converse argument not, we don't need to consider systems with codes that race below Shannon capacity, so that's fine. Okay, so we just need to think through how much entropy is generated by a single alpha noisy register. And let's say there's chi sub reg of such registers, then the total entropy is chi reg times the binary entropy of alpha. And now how much entropy can be dissipated by a gate? You can actually just do this computation for an AND gate or an OR gate. They have, let's say, equiprobable inputs. So there's 2 bits at the input, and there's 1/4 probability of one output and 3/4 probability of the other output. Right? So we go from 2 bits to log of 1/4, or I'm sorry, 1/4 log 1/4 plus 3/4 log 3/4, and that's 1.1887. So that tells us how much entropy a binary logic gate can dissipate. So these seem like kind of silly arguments, but actually doing the counting is needed to do the converses. Okay, so if we go ahead and do that, this is assuming noise-less correcting network, then we get a better bound. So we have Shannon's bound, but better normalized, not just the one, but also the logic gate's contribution. Okay, so we ensure stability by preventing this entropy accumulation, and we think of how much entropy had to be dissipated and counting how many logic gates it took. So this is basically a sphere packing argument. And we can compute that for my running example, and it is getting better. Okay. Now we can think through how much entropy is dissipated by noisy gates. And again, we can do that computation. Less entropy is dissipated by noisy gates because they insert their own. And now putting this result into the same sphere packing argument as before, we get kind of another bound on the storage capacity. Now we're normalizing but the Shannon part, the noisy, the entropy generation part, and then the entropy dissipation part. And finally, we get kind of an upper bound on storage capacity as a function of the component noise level. Here I had just used a single variable for the noise in the registers and the gates, but in fact, they're separate. So one can see which one contributes more to the capacity. So the effect of the gate noise is simply to change the amount of entropy a single gate can dissipate. And so what this expression indicates is that the storage capacity is much more sensitive to register noise than to gate noise. Okay, so when we're building these systems, the kind of system design principle is that we want to specifically focus on the physics of the storage elements and let the gates be as noisy, well, fairly noisy. Okay, so that's the circuit design principle that emerges. And we can tighten this gap quite a bit. So on the achievability side, by using degree distribution optimization for the LDPC codes. So for example, this is a better code than the 3.6 code I was just demonstrating. So it increases the storage capacity quite a bit and improves the gate level noise that we can tolerate. This black curve, this is the 3.6 code. This is for communications, we had optimized codes. The black one is Bazi's code, and the green one is something that's even better for communications. So in fact, there's a very open question in coding theory how to design optimal codes for this noisy decoder setting, which is completely open. Because the optimal noise-less code, the black one, is less good than some other arbitrary choice of code. Okay. On the converse side, we assumed that circuits would dissipate the amount of entropy given by the sum of individual dissipation ability of gates. But that's actually not true. So to tighten the converse side, we need to get a handle on the subadditivity of entropy dissipation. And that's where some of Pippinger's results will likely come into play. We also assume that dissipating only the entropy associated with register noise is possible, but we need to actually direct this dissipation ability in the right way. And so we need to get insight into the complexity of functional specificity, which draws on ideas from circuit complexity theory. And also we can think through some ideas from noisy control, right? So we have this dynamical system that we're trying to keep close to the origin. So we can think of that as open loop control and think through minimal realizations. And so there's very much an open question. This seems like a very straightforward question to ask. What's the storage capacity in the way I described? But we still have a large gap between the achievability part and the converse part. And so if we can actually close that gap, that'll be quite insightful. But yet we still had some design principles that emerged for circuit designers anyway. Okay. So beyond the Taylor problem, we can also push this entropy production dissipation argument to find fundamental limits of other kind of compute memory, these deep in-memory architectures, or associative memory, and also consider beyond-CMOS models. Okay, so those are some of the things that I think are kind of very interesting in this area from a mathematical perspective, but also from a system design perspective. Okay, so let me also talk briefly about another style of analysis, which is using the epsilon noisy model of von Neumann that also holds for spin electronics in asking the Pippinger, Hayek, Evans, Schulman type problem of how many, what's the circuit complexity we need to do reliable computation given how noisy the individual gates are, except that now we have energy. So we're thinking of these logic gates as having the property that their noise level decreases if we put in more energy. Okay, we have this chi function, a new chi function, which relates how the gate noise decreases as a function of the energy. Okay, and the basic question we want to ask is, can we construct a formula circuit, a tree-structured computational circuit, out of epsilon noisy gates that computes any given Boolean function with delta reliability at the system level for any input. So it's a worst-case characterization. And we want to be able to control the energy, not just the number of gates, but the total energy in the circuit. And the difficulty is in terms of this optimization, right? There are a lot of circuits with different levels of redundancy that realize a given function f. Right, if I want to AND two numbers together, there's so many circuits that can do that. If I want to compute the, I don't know, like the Hamming's distance between two binary vectors, there's so many circuits that can do that with different levels of redundancy. So we need to pick a circuit, but also for each gate in that circuit, we could allocate energy differently. And so there's also the allocation of energy across gates. And so this seems like a very complicated optimization problem. Choosing a network structure that computes a function f, and also choosing energy allocation across those gates that implement it. Okay, so how do we do that? It's kind of tough, it seems, right? But, you know, information theory to the rescue. Okay, so we want to achieve this objective. We want to minimize the total energy over all realizations that realize this function f. And we want to balance the redundancy in the number of gates in the chosen circuit against the energy allocated for gates in a circuit. Right, I think you can imagine two very extreme design points, right? You could have very, very large circuit redundancy and very little energy at each gate. So every gate is very, very noisy, but I have so much circuit redundancy. I have n modular redundancy, this and this, right? So that'll work fine. That'll achieve delta reliability. Or you could imagine another design approach where I give a lot of energy to each gate, and so it acts essentially noiselessly, and then it achieves delta reliability. But perhaps there is some intermediate design point in between, and that will perhaps optimize energy for our delta reliability. Okay. And so the approach we want to take is to optimize information theoretic limits to obtain KKT conditions on this problem, and then that'll yield the best structure and energy allocation. Okay, and the way we do that is to extend Pippinger's information propagation technique, which is a very nice idea from classical fault-tolerant computing, but here we're now going to be using energy considerations as well. So we'll relate the gate noise, the reliability, and the circuit graph, the network structure, using mutual information. And in particular, we'll draw on strong data processing inequalities for logic gates. Okay, so the basic idea, I think everyone is familiar with the data processing inequality, right? That the mutual information only decreases through some computation. Okay, but now we want to quantify that. How much does the mutual information decrease through a computation? That's a strong data processing inequality. And Pippinger had some bound as a function of the amount of noisiness in that gate. And then Evans and Schulman also improved it. And there's some more recent works by Wu and Polyansky that give even better strong data processing inequalities. Okay. So now we have this data processing inequality through a logic gate. And now we want to say, I'm going to try to propagate information through a larger circuit. So I'm going to go through one gate, then the next gate, then the next gate. So how much does the information decrease as I propagate the information all the way through the circuit? And that will upper bound how much information is mutual information between the circuit input and the circuit output. Right, everyone see that? Okay, in terms of the error probabilities of the gates. Okay, and so this is the kind of high-level idea of how we try to do this information theoretic bound. And this works fine actually for tree-structured circuits. I'll come back to how we do this for structures that are not trees, because then you'll have interactions and so on. Okay. Okay, so now we get that, and then we can write down the KKT conditions and actually get the best energy allocation rule. And it turns out that the optimal energy allocation is layer by layer, and you want to have the most energy at near the circuit output and the least energy near the inputs. And more specifically, the error probability should decrease like a geometric series along the depth with factor k to the beta over 1 minus beta, where beta is a property of that energy reliability function for specific gates that function. Right, so this gives us a very nice design principle for circuit designers. So if I'm building a circuit, I want to allocate energy in a way that it decreases exponentially or geometrically as I go down. Okay, so that's very pithy, very something that someone can actually use to build a circuit. And further, the optimization algorithm that comes up with the bounds is actually something one can implement, and it gives you a very specific energy allocation policy. And my postdoc Abhishek Chatterjee, formerly, who's now at IIT Madras, and Naresh's student Amaya, they actually implemented that, and they were able to show specific circuit designs that were quite close to the fundamental limits that were established through this theoretical framework. So not quite 0.00045 dB within the Shannon limit, but very close to the fundamental limits with a very practical circuit design. There's also further insights that emerge from this framework. First is that the minimum energy per bit is linear in the number of input bits, just like for noiseless circuits. So if you had restricted yourself to homogeneous energy allocation to all gates, like the older work of Pippinger and all, then you could not achieve energy per input bit that's only linear in the number of input bits. It would require a super linear amount of energy. Right? So this is very, very nice that by allowing this energy allocation across the circuit, you can actually achieve much, much better scaling laws with energy and reliability. And this is actually a physical property of these novel devices. So this heterogeneous energy allocation through a circuit is much easier in spin electronic circuits than it is in CMOS. And so that points to another reason why we would care to investigate these beyond-CMOS devices rather than just restricting ourselves to CMOS. Okay. Furthermore, that energy failure function chi is not super critical in determining the scaling behavior. And so maybe you don't need to worry about that as a physical device designer. At the systems level, we can deal with these things as we need to. right? But this idea that we can allow different electrical operating points in different gates is the key factor that allows you to go from superlinear to linear energy scaling. Okay, so what about networks that are not Boolean formulas, not tree-structured Boolean circuits? There's a lot of interest these days in deep neural networks, right, as this other tutorial suggests. So here we do not have a tree structure. We have a directed acyclic graph structure for feed-forward neural networks, so-called multi-layer perceptrons. And further, we might not want to implement this using Boolean gates, but in fact, so-called nano functions that might do a dot product and a thresholding or something like that. So more kind of larger devices that do bigger operations. And so you might ask, should we do the same kind of energy allocation? Should we have less energy in the devices up here and more near the output? Should it be the same geometric allocation? Will the mathematical technique work? Will that kind of information propagation technique work, even though things get mixed together now because of its directed acyclic nature? Okay, so that's the question we want to ask. And again, the formalization here is that we have binary multi-layer perceptrons. They're input to a neural network with plus and minus 1 as the inputs. There's a given connection pattern between neurons, real valued weights on the edges. There's an activation function like a sigmoid or a ReLU or something like that, which has, again, an output that's plus minus 1. The input to the activation is the sum of the outputs of the neurons in the previous layer weighted by the edge weights. So just a very standard multi-layer perceptron. And it has also a failure function. So a given neuron can fail independently of any other neuron with probability epsilon g, which depends on the energy consumption of that neuron E sub g. Okay, and again, when a neuron fails, it flips its output from plus 1 to minus 1 and vice versa. Okay, here we want to, again, define, we'll assume this function is convex, decreasing, and differentiable, and so has an inverse, like any physical function would. And again, we want to achieve delta reliability for any input configuration. So it's the same definition as in the Boolean case. And again, what's the minimum energy we need to realize? An input Boolean function using a delta reliable neural network. Okay, so now we need to extend Pippinger's technique in a non-trivial way. We have this directed acyclic graph. We have some number of neurons in each layer. And now we'll say for a given neuron G, let the set of paths to the output neuron be P sub G. Okay, so we have a given neuron in our network. We're going to say there's one path like this to the output, another path, right? So we want to consider that set of paths as P sub G. Okay, and now it turns out that we can propagate the strong data processing inequality through all the possible network paths and use Fano's inequality to bound the error. Okay, and so we have to actually just kind of do some interesting combinatorics of network paths through directed acyclic graphs to be able to get how many elements there are in P sub G. But after that, you can use the concentration kinds of arguments as for Pippinger's original approach. And so by doing this, you can actually get a bound for directed acyclic graph structured networks. Okay, and now again, we have the KKT conditions for the optimization problem. We want to minimize the total energy under the reliability constraint, which I've written in a slightly easier form. And again, we can work through the KKT conditions to find the optimal energy allocation. Again, as an example, if we have an exponential energy reliability function, which is the thermodynamic limit for CMOS, and also observed essentially for spin electronics, we find that we should allocate energy in a similar homogeneous manner, or heterogeneous manner, geometrically from layer to layer, but also weighted by the size of the layer. Okay, so we get, again, a very simple design principle that circuit designers can use directly. So allocate less energy at the top of the network, more and more as you go down. As a function of the ratio of the network layer sizes, you should essentially do a geometric allocation. Okay, so again, a very nice design principle that follows directly from the information theoretic optimizations. Okay. As a side note, just coming back to the biology, since it was kind of interesting, the optimization principle, the energy allocation, is essentially also observed in mammalian sensory cortex. So if you look up a lot of data on metabolic glucose rate in brain regions, the number of neurons in different sensory regions, and so on, the noise properties of quantal synaptic failure and other things, you find exactly the prediction that our theory makes. So it's suggestive that in systems with decreasing number of neurons per layer in hierarchical processing, this principle seems to actually play out. So here the brain-inspired design coincides with Shannon-inspired design for nanoscale implementations. Okay, so perhaps nature has found a solution similar to what we were suggesting to circuit designers. Okay, I'm going to go slightly quickly through this work on defect tolerance. This is work by Greg Warnell, Yuri Pilyansky, and their students at MIT. And here the idea is not to consider transient faults like we've considered throughout, but actually permanent failures. And the standard approach to dealing with this in the circuits community is to add spare components within circuits that allow you to recover from defects. But in fact, you can actually define kind of fundamental limits using Shannon theory. Okay, and this is, these are so-called static defects with reconfiguration. These are used in practice quite a bit, but there's been very little theoretical understanding. This is often used to abstract the design of ASICs and FPGAs, but I think it can also be used for RRAM structures. Okay, the basic idea, again, is that there's edges that represent a replacement line. There's primaries and spares. A spare can correct one defective component of the same type, but after it's been used, it's done. You want to find designs that are T-defect correcting and have the minimum trade-off in terms of number of edges and number of spares. And you can do basic repetition, so one spare for every original, which is quite inefficient, right? You have double the number of components now. You can have complete designs, again, fairly inefficient, but now you can perhaps use some coding schemes, essentially. So now you have a universal design for all types of choices. Okay. And now the basic result is as follows. So you can find a complete characterization of the fundamental limits for one defects, two defects, and arbitrarily many defects as a function of the noise properties. And these are in terms of the classic information theoretic functionals, for example, in Gallagher's book. Okay, and just to kind of give you a sense, this is the kind of average primary component fan out per defect and the normalized redundancy. And this is the fundamental limits. As you want more and more redundancy or reliability, you get a little bit of a decrease, but much of the region is captured by t equals 1 and t equals 2. Okay, and what also emerges is kind of efficient designs from basic coding theory. So kind of a Hamming block or other types of combinatorial structures that emerge from the design of small error correcting codes are quite effective for this problem. Okay, so just to kind of summarize, we've argued that a lot of techniques from information theory are actually useful for characterizing and optimizing nanoscale information processing, whether it was multi-terminal source coding analogies, joint source channel coding with neural networks,